Howdy and welcome to orientation. My name is Professor Peisel, and today I'm going to be talking to you about the energy analytics stream that is part of the Freshman Research Initiative here at UT. So first off, who am I? I am Professor Peisel. I am the research educator for the energy analytics stream. I started at UT in August 2019 after about 5 years in industry and government. My expertise is in geology, data analytics, and machine learning, and you can follow me on Twitter at geologyjesse. Our principal investigator for the stream is Professor Perch. Professor Perch started in August 2017 after 13 years leading research at Chevron. Professor Perch has an expertise in geostatistics, big data analytics, and machine learning. You can follow him on Twitter at geostatsguy, and you can also find all of his videos on YouTube as well. So now that we've talked pretty briefly about who we are, and I've introduced some terms such as research educator and principal investigator, let's go through and just define some of these terms so we're all on the same page for the rest of my presentation today. So the first term I want to define is a research stream. I mentioned that we are the energy analytics stream, and a research stream specifically is an undergraduate research group with a unique research focus. There's about 30 different research streams in the FRI, and you're going to be part of one of them. Next, we have a principal investigator. That is a UT faculty who oversees the stream. They are directing things at a high level and kind of focusing the research where they want it to go. Next, we have a research educator. That would be me, typically a PhD scientist, and teaches the stream courses and guides students on a daily basis. So I'm the one that you come to talk to about what we're learning in class, grades, all that sort of good stuff. And you'll probably interface with the research educator on a regular basis, but you'll most likely be talking to peer mentors for kind of odds and ends type questions. So peer mentors are students who completed the FRI course sequence, and they're helping mentor your group as you come in. So we have peer mentors that started in, 2018, 2019, 2020. They'll all be there to help you out and get you oriented for your first couple of semesters in the stream. And then the last thing on here is stream sort. You don't have to worry about it because we are a out of phase stream. So we start in the fall semester. Majority of the streams start in the spring semester. You're already placed, so you don't even have to worry about stream sorting at all, which is nice. So now that we've got these terms defined, just a brief note about your freshman interest group. So your FIG or your freshman interest group or your pod, make sure you add it with your quasi-unique number. You must have a clear schedule to add your FIG. Do not ever drop it. It cannot be re-added. Add your FIG first, and then you can add the energy analytics stream. For this upcoming fall 2021, our unique number is 52440. So that's our unique number for this fall. If you need to, you can switch sections of a course, really try and get your schedule kind of dialed around your FIG and the stream as best as possible. Math, if you are in FRI UGS 330, try to work around that course as we cannot switch you to a different one. So that's kind of a brief overview of FIGs, just kind of randomly here. Let's get back to talking about the streams and the FRI. All right, so we've got 30 different streams that are part of the Freshman Research Initiative. It's everything from data-oriented to biology to chemistry to robots, a little bit of everything in the natural sciences, which is really a lot of fun, seeing what everybody's working on. So we're down here in the bottom right. We are one of the fairly new streams. The stream started in fall 2019. And we are the only fully funded stream funded by outside donations from ConocoPhillips. So that's pretty exciting that we have that kind of funding. So what does the FRI look like from your perspective? So if there's anything you take away from today, I hope that's that the FRI is minimum a 2-semester experience. So for us, you come in the fall, you're registered in CS 309. It's a lower division computer science credit. And in the fall, you learn about how to do research, learn about machine learning, neural networks, how to clean data, how to use Python, kind of all the basics. And after your fall semester, you register for the spring semester. So you register for the spring semester. It's upper division CS credit, pretty hard to come by. It's CS 378. And in the spring, you conduct pretty independent research. Everything from machine learning to building out software. We've had a little bit of everything, generative networks, matrix factorization, data set munging. So it really depends for the spring semester. Let's say you get halfway through your spring semester, you're like, this is great, I want to keep doing this. Then you can come along in the summer. We do summer fellowships where we either continue research or start new research projects. You can volunteer in the summer. If you're really into it and your project warrants it, you can continue research into the fall. But really, kind of this left block here, this fall and spring, this is the core FRI experience. If you really enjoy it, come along for the summertime. And then after the summer, let's say you're like, this is great, this is really cool. Your sophomore year or your second year, come back in the fall, you can either continue research, you can be a peer mentor. This is where all our peer mentors come from. We've had a lot that have done summer. We've had some that have done both fall and spring. So it's really an opportunity to become a peer mentor. In the fall, spring of your sophomore year, you can join faculty labs, you can do REUs, internships. You can also do the Inventors program in the fall, which is where you take everything you've learned during this kind of first year and apply it to real world data sets. So you're solving business challenges that ConocoPhillips has in the Inventors program. Strongly recommend it. Very, very cool program. And then lastly, in the spring, typically, I think this year it was like March or April, we have the Undergraduate Research Forum where you get to present all of your research that you've been working on. So this is kind of what the student perspective looks like for the FRI. Now you're probably asking yourself, okay, this is cool, this looks great, we get to learn a lot, do this independent research. What is kind of the ultimate point of this? The ultimate point is that the FRI really prepares you to be a great job candidate. So a lot of employers, they want these skills like being able to communicate via both written and oral. You can do data analysis, you can work on a team, you're a leader, and you can organize and manage projects. Well, in the FRI, our students do all of these things. So you get the chance to write scientific reports. We've got teams that are right now, as I'm recording this, preparing their manuscripts from the spring for submission to journals. So you get a great experience at that. You can present at conferences. I've had one student present at an international conference. A whole slew of students present at the Undergraduate Research Forum. You get to analyze data that you either collect or scrape or are given. You get to work on teams. Teams are typically like 1 to 5 people. And then as a leader, you can work as a peer mentor, really hone your leadership skills, which is really cool. And then you can also learn to manage your own project. So figure out your research goals, orient it, and then keep track. Are you going to go waterfall? Are you going to go agile? How are you going to manage your project? So really, being part of the FRI prepares you to be a great job candidate. Now, you're probably thinking to yourself, okay, this sounds great. I'm on board. This is really cool. What exactly is the energy analytics stream all about? What do you actually do? Let me tell you what the energy analytics stream does. So we're primarily focused on energy in all forms and how can we provide it to humanity. Seems like a very large, open-ended problem. So this spring, we had 3 groups that were focused on generative neural networks, and they were interested in, one, how can we make architectures more efficient, consume less energy that way? And then we had 2 groups that were focused on how can we denoise data. So in the subsurface, denoising seismic data, denoising borehole imaging is going to be key to both oil and gas as well as geothermal reservoirs, being able to minimize the kind of fuzziness in our data. So we had 2 groups work on denoising images. And then we had 1 group focused on reinforcement learning and 1 group focused on matrix factorization or recommender systems. So today I'm going to share with you kind of briefly what they worked on this spring and get you a little bit fired up for what you can expect. And remember, these are all brand new freshmen that came in just like you last fall, and this is what they worked on and built out this spring. So the first group we had was looking at how can we efficiently build hyper-resolution images from randomness, more or less. So this team figured, well, we can make it more computationally efficient by using kind of different stages of generative neural networks. And they focus primarily on generating human faces because there's a lot of data for that. So it seemed like a fairly reasonable task. So their idea was, first we'll generate the outlines of faces, kind of like you would draw an image of a face, if you were just to draw it by hand. So they created a generator that creates kind of these outlines in the bottom left here. And then they created a generator that kind of fills in the details. It does a really good job filling in noses and eyes. It kind of has a strange issues kind of around the edges, but it fills in kind of these details. And then that output is then fed into a generative network that colors it to make it look like a person. So it went from edges to grayscale to color. And you can see, for hyper resolution, it didn't end up being as good as we expected. But that's kind of one of the things about research you learn about along the way, is that sometimes things work, sometimes things don't work. So this worked, but not at this resolution that we had hoped for. But very cool. These students all had a great opportunity to interface with the supercomputer on campus and really learn all about generative networks. Okay, so then our next 2 groups were focused on denoising images with generative networks. So the first one, team 1 was really interested in how can we remove white noise. White noise is really tough to characterize. How can we remove it and more or less recreate the image? So they used some pre-trained networks and trained it on different levels of noisy images. So on the left-hand side, they trained a model with 55% noise. On the right-hand side was 70% noise. And pretty interesting results. Again, they used pictures. I think this is the Celeb A data set because it's like 100 and some odd thousand images of people. So it was pretty easy to get at, and conceptually what they were thinking about is this is kind of like CSI's Enhance, where they have that really blurry picture of somebody and they say enhance, and it keeps getting better and better. This is kind of what they were working on. What's really interesting is that it does, like this one on the left, the 55% noise, does a pretty good job making predictions at 55%. Above that, it gets kind of weird, which is kind of cool. And same with the 70% noise. It does all right at that level, and below at 0% noise, it's kind of weird. It's not sure what to make of it or what to generate. But it does a little bit better when it's trained on higher noise levels. So they learned a lot. Really kind of a cool experiment to see, is this possible to more or less find the structure underneath the noise and be able to pull off that noise and regenerate the structure. Does a pretty okay job. You can see in the backgrounds, it gets the poses somewhat okay, but by 80% noise, it kind of struggles with it. So again, this team was focused on denoising images, and the application of that, again, in the subsurface. We need to denoise things. And you might see here in this next one for team A, they were also denoising, but they, instead of doing just straight up images, they were removing these stripe noises that you can see here from ground penetrating radar from Antarctica. So what we have here is they basically fly over Antarctica and shoot radar into the ice to measure how thick the ice is. So here in this image that my cursor is on, this is all ice here, and then this is the bedrock below. So these are all ice layers and then bedrock. And so what this team wanted to do is see if their original goal was, can we remove these kind of this noise? And they did a pretty good job of that. And then their second goal was, can we just more or less interpret the subsurface? So can we highlight this whole region where this is bedrock, this is kind of our transition zone from ice to bedrock, this is all ice, this is all ice. So they more or less have an automatic interpreter of what's going on in the subsurface. So pretty cool project. You can see on the left, this is our radar-gram, so this is all ice, and then our bedrock here, and then our corresponding bedrock layer here, ice, like kind of our transition zone, and then our ice layers up above. You can see as it gets kind of into these way more noisy zones, it kind of struggles with it, but it does okay. Not super great, it just kind of hangs on, but it does okay. So that's what this team was really focused on was, can we denoise these? Can we automatically interpret them? And to what extent? So really cool project. So those are our three kind of generative network projects that we had this spring. Our next group worked on reinforcement learning. So I came to them and said, let's work on spatial reinforcement learning. And they said, okay, can we figure out where to put electric vehicle charging stations? And I said, that sounds really cool. So what this team ended up doing was they found a data set out of the state of New York, and they focused in on Albany, New York, because it kind of makes a nice grid, a little easier to deal with than New York City. And they went through and first they made predictions. So demand predictions, how much energy is going to be consumed at each one of these grid locations. So that was their first pass. Okay, they've got demand predictions at every single location. And then they went through and said, okay, where are our current existing stations, our charging stations, which are these little green dots on this map on the right-hand side. And then they took their agent, their reinforcement learning agent, and said, okay, figure out where the best place is. They're the most optimal places to put charging stations. And at first it kind of started off fairly random and eventually started placing things in a more reasonable set of locations. They compared it with random placements, with grids, just to see how it does compared to either just gridding out the locations versus randomly placing chargers. And the agent actually does better than random and does better than just kind of gridding out and putting a station in set distances apart. So pretty cool. This group, actually all the groups are prepping their manuscripts that they wrote up. They wrote up a full manuscript of what they did. And so they're prepping them and are going to submit them to a journal here in the next probably 4 to 6 weeks would be my guess. So pretty exciting. I think this one's a really novel use of this data set and technique. So pretty cool. All right, our last group this spring worked on matrix factorization, or as you might know it, a recommender system. So I came to this group and said, hey, let's use matrix factorization to interpret things in the subsurface. And they came back and said, well, can we use it to recommend wells for companies to buy? So right now in the oil and gas industry, acquiring other companies, acquiring abandoned wells or orphan wells is kind of a big deal. And this team came up with this idea, said, let's take these wells, take these operators, and then just figure out which wells each operator should buy. And so they ran through with just wells and operators, and then started adding in auxiliary features like location, depths, formations, and other well characteristics. So they came up ultimately a list with every company gets 10 wells that they are recommended to purchase, and they can compare how good or how bad it did. So this one's really, really interesting, novel use of a recommender system. So pretty cool research project. I think it's a great use of the technology rather than having to pay somebody to sit and figure out, okay, these wells are similar to what we've got, they're kind of by our acreage. This just automates it, takes care of that. So those are the research projects that they worked on this spring. All these students came in, learned about machine learning, how to code in Python, and then just went wild this spring with these cool research projects. So in a more general sense, our stream goals, what I hope you walk away from this class with is learning how to use data analytics, geostatistics, and machine learning to make predictions on real-world energy data sets, be subsurface, electric, whatever you want, as long as it's energy related. And then at the end of the spring semester, you should have a code base or something that if you want to deploy it or redo the workflow that we can just run through and read, more or less replicate your entire workflow from. So pretty useful for not only learning things, but also at the end of the day, having something to show for this project that you worked on. So pretty cool options as far as projects go. And with that, thank you for coming to your virtual orientation. If you have any questions, please email friadmissions@utexas.edu. Or if you're on campus, you can stop by the FRI office in Painter Hall. It's in Painter Hall 3.04. If you want to have questions, you're on campus, you can swing by my office. I am in Painter Hall. I'm in Painter 2.08B, so pretty much just straight downstairs from the main FRI office. So that's the best way to get questions answered. Send us an email, stop by the office. Also, you can connect on Facebook, LinkedIn, Twitter, YouTube. Send us your questions. We would be happy to answer them. It's going to be a great fall semester. We're going to be back in person, talking about machine learning, subsurface, energy, and solving the tough challenges of tomorrow. So with that, thank you, and I'm looking forward to meeting you all.